Okay. Are you familiar with what I'm writing? When I just consider front and the back, and the fluid which is coming minus the fluid is leaving my surface. So this is, and this increment because one surface is located in this coordinate and the other one is located in this coordinate. So this minus means the net. So if I calculate this, but to calculate this, you have to be very careful because these functions are evaluated in the very yes.
What about the angle?
I already considered the angle, you know, fx. When I write the fx means that only the component in the x direction have the contribution to the front and the back. And when I write fy, it means that to the right and the left side only the fy has a contribution. For that, I can use the Taylor series. So it will be partial fx delta x over 2 minus partial fx minus delta x over 2, of course, plus another correction, plus partial fy. Of course, all will be computed at this point. This is a Taylor series. Of course, you have the terms which delta x squared, delta y squared, and delta z squared. But you can forget about that. And you know what we find? We find that it will be partial derivative of x plus partial derivative of the y component, partial derivative of z component evaluated at this point, multiplied to dx, dy, dz. What is that? This is the volume element. This is the volume of this cubics. So, very interesting. I find the flux, the normal flux, like the volume, multiplied with the quantity which we can call it divergence F. So divergence F will be limited because all this delta x should. I want to find the divergence for the change of the vector at the one point. So if I divide the f dot this to the volume and take the limit, you will find the divergence. This is the real definition of divergence. Of course you know that before, because we wrote this before, how to calculate. But what does it mean? It means that the flux per volume. Flux per volume is the, of course the volume should, this is the definition of the divergence. Keep this definition seriously, because this definition is independent from the coordinates. I mean, I did this calculation in the Cartesian coordinate, but you can repeat that for any coordinate. Especially we will do the calculation in the curved space when you have the different coordinate, not the Cartesian coordinate. So this is the real definition of the divergence. For the curl also, for the curl, you need to consider the again you have a vector field, and you need to consider the linear integral of that around the small cubes, like again y is minus y squared, sorry, x, and x squared plus delta x squared, and this coordinate will be y squared plus delta y squared, and then y square minus delta y square in the one plane. And you have the another plane xz, and you have another plane yz. For each one, if you calculate f dot ds, you will see that you will find the definition of the curl. So you will find, that I will not do because it will take a lot of time. Multiply to the area. Of course, when the limit of the area tends to the 0. Area in each plane. For example, if you do this calculation in the xy plane, you will have here delta x, delta y, and you will find the perpendicular or vertical component of that. So here you will get the z component of the curve. For me, it's important you get the first idea of the divergence. To find the divergence, you need the geometry and you need to find the flux. So this is also like a flux, but this is not a flux, this is a rotation of the disk. This integral means the rotation of some kind of the fluid. Because it looks like that you are going to calculate this integral over some path. Huh? Yeah. Delta S is one-dimensional path, actually. So this is like a rotation of the fluid. So it gives you the curl. So curl can be defined like a limit of the circular. So curl F will be limited delta R tends to 0, integral of f dot ds over delta R. For each component, I write that because you can find the curl component x, component y, component z by considering the circulations of the vector field in the plane. This is the circulation integral. Yes. Circulation.
What is the physical meaning of divergence? Because the curl is rotation.
Yeah, divergence means that how much the field line are going to be close to each other. If you have a divergence positive, it means that they are going to be diverged. So they are going to be far, splitting or be very different from each other. That's far. For example, this picture gives me the divergence F is negative. Because they are going to be close to each other. Yeah, that's the whole. If you want to make it more physical, you know, when you have a sink, you have the negative divergence because everything went. And if you have the opposite of the sink, I don't know, opposite of that, like volcano, for example, you are familiar with volcano because geophysics. If you have a volcano is the divergence positive. So if you can model, look just one sentence. If you can model the volcano in terms of the vector fields, you can predict that when the volcano started after some time, which points will be. I don't know if such modeling exists or not, but by mathematical physics, actually, you can model everything, as I told you. You just needed to focus on and find your problem. And because we have already the material is just the vector field and these things. So I want to back. So the things which we will need in the potential theory is the Sturgovsky theorem. I will back to the Laplace equations. I want to use the Gauss-Sturgovsky theorem on that and give some fact about these equations. Can I write this equation divergence and gradient phi 0? I want to take the volume integral from that. Okay. If you take this as a vector field, as we take before, divergence f is integral of f dot area. Yes? Area means that you have a surface, yes? Area always is a vector, as you know. Direction is n, for example. If you are inside this room, so this surface has the direction vector to you. If you are standing on the roof, so the vector goes outside. So can I write that n dx? And this object, gradient phi dot n, is called a directional derivative. And what does it mean? It means that how much phi change in the direction of n. Yeah? That's exactly the meaning of that. So if this is a gradient phi, it means that how much of this will be in the n directions. This is, we normally show that by partial f to the n. I writing this because in next lectures about potential theory, I will use partial f phi versus n, and you need to be familiar with these notations. Okay. But if Laplacian is 0, so it was a 0 at beginning, so this will be 0, huh? For any surface. Because I started from Laplace equations. So we find interesting equation is that solution of Laplace equation always should satisfy these relations. The net flux of this vector field will be 0 always. What is this vector field? Gradient phi, if you think phi as electric potential, gradient phi is electric field. It means that the net flux of electric field will be 0. If there is no source. Because this equation was when rho was 0. You remember the Poisson equation. Keep it these equations because we will need that later. How many dimensions you have for, in real problem we have just 3 coordinates. As I told you, we will use potential theory in electromagnetism. Of course we have a time, but we will do something else with time. Fluid dynamics, for example, is just working with 3 components. The fluid is going in 3 directions, or normally in 2 dimensions. Because the channel is, the one side of the channel normally is considered ignored. So I want to give you one interesting fact about the solution of Laplace equation in 2 dimensions. So we almost now start to solve the Laplace equation before I give you just the information about the solutions. So the first part which I will start here is solving Laplace equation in 2 dimensions. 2-dimensional space. So, by many reasons, 2-dimension is very important for us. First of all, 2-dimension is an approximation from the 3-dimension. If you consider the third direction as a tiny parameter. For example, if you have a pipe, and the pipe is very long, no. Yes, that's exactly the same. Yeah. If you have a pipe and the pipe is very long in comparison to the size of that, for example, R, when the fluid is moving on that, so the question of where the fluid is locating or where you are standing is not important because this is very long. For you, just important the coordinate in which point here you are standing actually. So the problem will be 2-dimensional just. You can forget about the 3 dimensions. Or also if you consider the fluid on the very, very thin surface, in thin surface, you have just 2 dimension, and you can forget about the Z. This is the, for example, in condensed matter, it is like a graphing 2-dimensional surface. The third one is considered very tiny parameters. So I want to give information about how to solve these equations. Before I give you the technique to solve the equations, I want to demonstrate one fact, is that this is the theorem. In 2-dimensional Laplace equation, the potential never reach extremal values. Extremal means maximum or minimum. Very strange. It seems that if you have it, this is your system, okay, this channel or anything you want to, and you are looking for the solution for that for some reason. For example, you are looking to find the potential, electric potential, or the fluid potential. This theorem say that as long as Laplacian is 0, the potential never get any maximum or minimum. It's very important because
in equilibrium?
yeah, no equilibrium can be happen in the system when you don't have any charge. Never can be equilibrium. Yeah, this is call it in electrostatics. This call it the Kelvin theorem. So I think Kelvin theorem in electrostatics. But we don't give it the name. The theorem is that 2-dimensional Laplace equations never get maximum or minimum. What's the proof for that? To have, we consider that there is a maximum or minimum in this point for this function. Okay. So to have a maximum or minimum, the first condition is that the first derivative of this function should be 0. Yes. Yes. We think that we think that it exists this point. Okay. So now I want to show that this point cannot be positive or negative. This point cannot be maximum or minimum. I mean, you never can have it like that near this point. You never can have it, or minimum. You never can have it. I want to ask you, do you know how we can test that a point is maximum or minimum of the function with more than one variable or not?
Second derivative?
Yeah, second derivative, positive and negative, work for one variable, yeah? When you have fx, for example. For the two variable, you needed to check more than second derivative of one parameter. You needed to check the second derivative of the this is the quantity which you needed to check that. And if this quantity is positive or negative, so after that you can say that this is there is a stability of the maximum or minimum here or not. You know, forget about the 2-dimension. In 1 dimension, to have the minimum, what do you think? To have the minimum, so the second derivative should be positive. Yeah? In one variable. If you have just phi x, this means that you have the minimum here. So second derivative of this, at least in this point, should be positive. And if you have that, second derivative of that, negative, and if you have a 0, so it means that you cannot decide about what is that, the situation. In second derivative, in 2 variable, instead of the first one derivative, you have a combination of the second derivative of x, y, and this. If you want to find this, you can check any calculus book, calculus 2 I think or 3, yeah, about the second two variable functions, multivariable function. You can find it there. I don't want to back that. I think it's not easy, not difficult to understand that this is a generalization of that. Why we have more than one derivative? Because you have more than one variable. So I consider all the combinations. So so I need to evaluate this determinant, and you see that it's going to be 0.